The artificial intelligence industry is facing a pivotal moment. Training large language models, or LLMs, has become more expensive, energy-intensive, and time-consuming than ever before. With the demand for smarter AI growing, the computational requirements have soared to astronomical levels, often costing millions of dollars and leaving a significant carbon footprint. NVIDIA's latest innovation, NVFP4, promises to change the game. This new 4-bit floating point format could transform how we train the next generation of AI models, making the process faster, cheaper, and more sustainable. Let's dive into how NVFP4 is setting a new standard for AI training. Training neural networks involves billions of calculations on massive datasets. Traditionally, these computations use 16-bit or 32-bit floating point numbers, which are precise but consume a lot of memory and computational power. The industry has gradually shifted toward lower precision formats to save resources. FP32 offers maximum precision but is slow and memory hungry. FP16 and BF16 strike a balance and are widely used. FP8, now mainstream, doubles the speed over FP16. Now, FP4 4-bit precision emerges as the new frontier, promising up to 3 times the speed of FP8. But this leap comes with unique challenges that must be addressed for stable AI training. While 4-bit precision sounds promising, it introduces significant hurdles. At such low precision, numerical errors can quickly accumulate. Gradients, the signals that guide learning, may explode, vanish, or oscillate, making training unstable. 3 main problems arise: limited dynamic range, quantization bias, and outlier dominance. With only 4 bits, representing both very large and very small numbers is nearly impossible. Rounding errors can systematically skew values, corrupting learning signals. And a few abnormally large values can dominate, squeezing other values into a narrow, less useful range. Overcoming these issues is crucial for making 4-bit training practical. NVIDIA's NVFP4 format introduces several technical breakthroughs over previous 4-bit standards like MXFP4. NVFP4 uses smaller 16-element blocks instead of 32, allowing for finer-grained dynamic range capture. It also employs E4M3 scale factors, which provide 3 mantissa bits for better fractional precision. This approach eliminates wasted representable values and preserves more of the data's dynamic range. Additionally, NVFP4 uses a 2-level scaling strategy. Per block E4 M3 scales for local variation, and per tensor FP32 scales for global distribution. These innovations enable NVFP4 to reach target validation loss with 36% fewer tokens than MXFP4, dramatically shortening training times. NVFP4's efficiency is unlocked by NVIDIA's Blackwell GPU architecture, which provides native hardware support for 4-bit operations. Specialized tensor cores handle the entire quantization pipeline. They read narrow 4-bit inputs, apply 8-bit block scale factors, compute partial dot products, restore original magnitudes, and accumulate results in FP32. This tight integration of hardware and software eliminates the typical overhead of low-precision computation, making NVFP4 not just a theoretical improvement, but a practical one. The result is a seamless, high-speed training process that leverages the full power of modern GPUs. One of the keys to stable 4-bit training is not treating every layer the same. NVIDIA found that certain layers, especially those near the output, require higher precision for numerical stability. In their 1-2 billion parameter model, the first 2 blocks and the last 8 blocks use BF16, while the middle 52 blocks use NVFP4. This selective approach preserves most of the computational savings while ensuring the model converges reliably. Ablation studies confirmed that even keeping just the final 4 blocks in higher precision maintains stability, suggesting future optimizations could push even more layers to FP4. Outliers, extremely large values, are a major problem in low-precision training. NVIDIA uses random Hadamard Transforms, RHT, to redistribute these outliers across all dimensions, resulting in a more balanced, Gaussian-like distribution. This technique is applied only to weight gradient computations, using a 16x16 matrix for efficiency. The transformation is fused with other operations to minimize memory overhead. Importantly, Hadamard transforms are not used in forward propagation or activation gradients, as they don't provide measurable benefits there. This targeted approach helps maintain stability without unnecessary complexity. A subtle but critical issue in low-precision training is the chain rule violation caused by tensor transposition. When a weight matrix is used in the forward pass and then transposed for the backward pass, standard 1D scaling can produce inconsistent quantization. NVFP4 solves this with 2D block scaling for weights, using 16x16 blocks ensuring identical quantized representations in both directions. Activations and gradients use standard 1x16 scaling. This approach preserves the mathematical integrity of the training process and prevents loss degradation due to inconsistent quantization. Traditional rounding methods introduce systematic bias in low-precision formats, especially for gradients. NVIDIA employs stochastic rounding, where values are rounded probabilistically based on their distance to the nearest representable numbers. Over many updates, this approach ensures that the expected value matches the original, unrounded value, eliminating systematic bias. Stochastic rounding is applied to all gradient tensors, but not to forward pass tensors, where it can actually cause instability. This selective application is crucial for maintaining learning signal integrity in 4-bit training. NVIDIA validated NVFP4 by training a 1-2 billion parameter hybrid Mamba transformer model on 10 trillion tokens, the largest 4-bit training run to date. The results are impressive. During the stable phase, the validation loss was within 1% of FP8, and even during the decay phase, the gap widened only slightly to about 1.5%. Across reasoning, mathematics, multilingual understanding, and common sense tasks, NVFP4 matched FP8 performance. Only coding tasks showed a minor gap attributed to evaluation noise. This demonstrates that NVFP4 can deliver high accuracy at unprecedented efficiency. To highlight NVFP4's advantages, NVIDIA compared it head-to-head with MXFP4 using an 8 billion parameter model on 1 trillion tokens. NVFP4 reached a 1.5% relative loss error at 1 ton tokens, while MXFP4 needed 1.36 tons tokens to achieve the same quality a 36% longer training time. This efficiency gap translates directly to cost savings. For example, if training costs $10 million, NVFP4 can save about $3.6 million compared to MXFP4. At hyperscale, these savings become transformative, making advanced AI training more accessible and sustainable. NVIDIA conducted systematic ablation studies to test the importance of each technique. By removing one component at a time from a fully trained checkpoint, they observed the impact on training, stability, and loss. The results were clear. Removing stochastic rounding caused severe instability. Omitting Hadamard transforms led to outlier problems. Skipping 2D scaling increased loss, and reducing high-precision layers caused divergence. These aren't optional optimizations, they're essential for stable, large-scale, 4-bit training. Interestingly, smaller models on shorter runs were less sensitive. But as models grow, every component becomes critical. The shift from FP8 to NVFP4 brings substantial real-world benefits. Computational efficiency improves by 2 to 3 times, with a 50% reduction in memory bandwidth requirements. This means models can be trained in 40–60% of the time, dramatically cutting costs. For instance, a model that costs $100 million to train in FP8 could cost just $40, $60 million with NVFP4. This democratizes LLM development, enabling smaller organizations to participate. There are also significant environmental benefits, with proportional reductions in energy use and carbon footprint, making AI development more sustainable. For applications demanding the absolute best accuracy, NVIDIA suggests a hybrid approach. Switch to higher precision during the final training phase. By transitioning to BF16 for the last 18% of tokens, models can fully recover FP8 level loss. Even switching just 1% before the end provides significant improvement. Most of the benefit comes from higher precision in the forward pass. This strategy allows organizations to tune the transition point based on their accuracy needs and computational budget, balancing efficiency and performance. NVFP4 is supported in NVIDIA's open-source transformer engine, making it easy for developers to adopt. The library offers automatic quantization, seamless integration with PyTorch and JAX, configurable mixed precision policies, and built-in Hadamard utilities. Full NVFP4 acceleration requires Blackwell GPUs, GB200 divided by GB300 series, and CUDA 12 or higher. While emulation is possible on older architectures, native speedup is only available on Blackwell. This makes NVFP4 accessible for both cutting-edge research and practical deployment, paving the way for widespread adoption. NVIDIA's NVFP4 isn't just a technical achievement, it's a paradigm shift for AI training. By demonstrating stable 4-bit training on a massive 1-2 billion parameter model, NVIDIA has challenged the belief that high precision is always necessary. The holistic methodology combining mixed precision, Hadamard Transforms, 2D scaling, and stochastic rounding proves that every component matters. The immediate impact is faster, cheaper, and greener AI training. Looking ahead, as NVIDIA refines this approach and scales to even larger models, NVFP4 could become the new standard for AI development, making advanced AI accessible to more people and organizations. The era of practical 4-bit training has arrived, and it's transforming what's possible in artificial intelligence. NVFP4's combination of speed, efficiency, and accuracy opens the door to larger models, faster experimentation, and more sustainable AI development. As the industry adopts this new standard, we can expect rapid progress in AI capabilities, with benefits reaching far beyond the lab. NVIDIA's NVFP4 is not just a breakthrough, it's the foundation for the next generation of AI innovation.